Hello, this is Jack Anthony, and in this video, I'm going to introduce forced motion, rendezvous, and proximity operations. And we're going to cover in the first two slides, do a relative motion review of the natural relative motion we did last time in the video series, and I provide the links right here. So if you can get on YouTube, you can get 24 minutes of awesome natural relative motion education. Then I'm going to, the next two slides, introduce force motion circumnavigation about a target. I'll introduce waypoint proximity operations. That's the technique we use. And we'll take a look at the force motion circumnav in the RIC frame. We'll also look at the benefits and challenges of force motion. So you've met the RIC frame. There it is, RIC, right there. It's the preferred relative frame for relative motion, and it's easy to understand. At least I think it is. It's attached to the target, and it has an axis that goes away from the Earth or up. That's radial. In track is the direction you're going, and cross track is, in this case, out of the paper. It completes the right-hand set. The motion of the chaser is relative to the target in this RIC frame. So let's press on and review natural motion circumnav. Now you're probably looking at this and going, oh my gosh, what is all this? Well, it's a depiction of the natural motion circumnav in three two-dimensional senses in the RIC frame. What we concentrated on last time is this frame, the radial in-track. Okay, that's the most popular. Most every drawing is in that way. You saw that there was a, in this case, a downward radial burn, and then it caused this motion. Now we're out at geo, so we're 42,164 kilometers from the center of the Earth, and every 24 hours it'll do this. Okay, see that? So last time we went over the inertial view, but we're not presenting that this time because you're all experts in relative motion. So what I wanted to show you here is that we're gonna change it up a little bit. We're gonna add a little cross-track burn component so that here at the 6-hour point, we're plus 10 kilometers to the north and in the positive C direction. And then up here, when we cross here, 18 hours after the delta V, we're 10 kilometers to the south, to the negative. Okay, so it kind of tilts the NMC over. Well, we can see that in these diagrams over here. This is the cross-track, in-track coordinate frame. Okay, we're looking at it in that depiction. R is into the paper. So for the delta V, it can't just be pure radial. We need a little cross-track component, and that's why it's 1.05 meters per second total. It's kind of done at an angle. So we fire the thruster, and this is what it sounds like. That sounds really cool, doesn't it? It moves into the positive cross-track to the 10-kilometer distance when the in-track is 0, when we cross 0. See, that's right over here. We're down in the radial, but here we're depicting cross-track. So there's the positive 10, then we cross the I-bar. That's right over here in this depiction, and then it comes back through the negative cross-track at the 18-hour point. So over here, it's 10 kilometers into the paper. Okay, you see that? So this is cross-track, in-track. Down here, this is a really nifty drawing. This is radial cross-track. So what you see in the radial is it goes negative, but it also goes to positive 10. That's in 6 hours. Then it takes 12 hours to go way over here. So now it's positive 10 in the R and negative 10 in the cross-track. So all this here tells the complete story of what's going on. A lot of people prefer 3D diagrams, satellite systems toolkit depictions, but this breaks it down into the components in the RIC frame. So I wanted you to see that. Review done. Here we go. Now we're going to look at a force motion circumnav. This is where instead of one single burn, we do multiple burns to complete a circumnavigation about a target. In this case, we're going to try to stay as close to 10 kilometers distance. So instead of starting out at 20, we are going to move into 10, and then we're going to start this journey you see here, and I'm tracing it out right now. Okay, so this is a 10-kilometer force motion circumnav. It uses four little delta V's. The total delta V to complete this journey, this 24-hour journey around the target, is 3 meters per second. Costs a little more, okay? Like we did in the tilted natural motion circumnav, we're going to be 10 kilometers positive on the C here and negative 10 here, so it's tilted over. Now you're probably wondering, what's all that yellow stuff right here? Look at that. Look at that. Whoa, look at that. Well, what that is, it's the free flight trajectory. And that is the trajectory you do not want to be on. Let me just show you an example. We're going to start the FMC from here, and we're going to journey around the target, maintaining a 10-kilometer distance for a 24-hour revolution period of the FMC. Okay, so listen as I go through this. So we start here, and we burned a little hotter, so we're on this blue trajectory. Everything's going good. We get here. It's 6 hours since we started the FMC. If we do nothing, we're going to scooch off this way, and that's not our intent. So at 6 hours here, we're going to do another delta V. That's what it sounds like. So now we're on this blue path, and 6 hours later, we cross the I bar, we're here. So it's at 12 hours. If we do nothing, we're stuck on this free flight trajectory. We don't want to do that. Don't do that. So here we go. We're now moving on this trajectory. See how we're forcing the motion with these burns, these additional burns? We cross the R bar, we're at 18, and we want to get back to this point. So guess what we do again? We do a delta V, a small one. And now we're on our way here, and we arrive back here. So this is a 4 burn sequence. You can do more if you want. Costs 3 meters per second, a bit more than the NMC, but we maintain this 10-kilometer distance for the most part. So that's just really cool. Here we go again. Delta V. 6 hours later, delta V. 6 hours later, delta V. 6 hours later, we're at the 18-hour point. Guess what? We burn again. We come back here. If you want to keep going, you better do something. Keep going. Do another lap. Okay? Don't do this. That's a free flight trajectory. So you may ask, well, can we go faster? Heck yeah, we sure can go fast. Here we go. Over here, what if we go fast? We're going to do the 10-kilometer FMC with 10-kilometer max cross-track. If we want to do that whole lap in 12 hours, it's 5.6 meters per second total. What if you want to do it in 6 hours? That's 14. What if 4? Man, that's smoking. Whoosh, all the way around there. 22 meters per second. So these burns would be really bigger to really wing around that target. So that's how that works. Okay, get ready for this. We've seen this in the RI. What's it look like in the other depictions? Well, you know this stuff. Here we are in the RC. So we leave here, we swing out here to the positive C. Now it's not a straight line, it's got a little curve to it. We hit here, and now we start heading back this way to the 18-hour point. We're now negative 10 kilometers, and we're positive 10 R bar, and then back we go here. Oh yeah, we don't forget we need a burn here. So, and then we're back here. If you want to do it again, keep doing the burns. This is motion in the R and the C. This here is motion in the C and the I. So this is positive I, this is positive C. So you do the burn, you swing out to positive 10 C, but now you're 0I. Come through here and then burn again. You got to burn here, got to burn here, got to burn here. And that makes this rather odd shape here. Okay, so R I is the typical way we do this, but if you want to get an idea of the 3 dimensions, you've got to look at it in the RC and the CI. Okay, and I want to give credit to Palsky and Associates who teach the advanced RPO course to especially the Delta 9 folks. This is using their waypoint planner. Okay, so this stuff is just really fun. Well, I'm going to wrap it up with a little bit of a conclusion. Here we go. So, as you know, the first rendezvous was accomplished by the United States, Gemini 7 and 6, in 1965. Here's a picture. The mission most special to me, well, they're all special, is XSS-11, 2005 to 2007. It was America's first journey into low Earth orbit rendezvous and proximity ops. So, you've now completed natural motion and forced motion, relative motion educational sessions. So comprehending astrodynamics can be fun. It is fun. I like it, but it takes grit. Well, you ask, what's grit? Well, grit is the passion to learn. So, hey, learn this stuff. Ask some of the people you work with about it. There's a lot of people in the NSTC who know this stuff. It takes passion and perseverance. You just got to keep thinking about it. Go back and look at all those plots. It makes sense. At least to me it does. Good luck. You're doing great things for America, and that's important. And I encourage you to be tough and competent, because that way there, no one will ever mess with us, and we'll be the big power in space, and armed with this astrodynamic knowledge, we will be awesome, most awesome. Thank you very much. Hope you enjoyed this.